Bismillah ar-Rahman ar-Rahim. Alhamdulillah. Wassalatu wassalam ala Rasulillah. Today is a very important topic in chapter 9. You know, chapter 9 is all about the steady state solution, right? So this topic for today, a lecture, how to find the steady state solution directly without going through the total solution. This is the topic of today, okay? For example, remember this problem from chapter 3. You have a mass, spring and damper system with external force, sinusoidal function. This is the forcing function, right? Single degree of freedom system. This is second order system. What I'm looking for here, I'm looking for the steady state solution only. I want to solve for the steady state solution only. Okay? And also draw the steady state solution. Okay? This is what I'm looking for. All right. Now, the method that we learned so far in chapter 3 is to go through the total solution. Solve using a Laplace transform. Okay? Take the Laplace transform, expand, partial fraction expansion, inverse Laplace. Okay? It's going to be very long. Okay? You need 2 pages at least to solve this problem. And at the end, you will have the total solution, the complementary and the particular solution. In other words, you will have the transient response and the steady state response. We need only the steady state response. I'm not interested in the transient. Is the question for today. The question for today. Is there a method to solve directly for the steady state solution without going through the total solution like we did in the last example? The answer is yes. How? Sinusoidal transfer function. Okay? Using the sinusoidal transfer function. This is the method that we will talk about today. How this method is working, okay, or how it works. First, there are 3 steps, okay. The first step, obtain the transfer function, get the transfer function. You know, the input will be always your forcing function, right? The sinusoidal forcing function or the harmonic forcing function, the external force. It's going to be always your input. The output will be your displacement if it's a mechanical system, second order system, okay. So get the transfer function. This is what you need to solve. Then step number 2, get the sinusoidal transfer function. The sinusoidal transfer function, just plug in, instead of S, plug in J omega. This is the frequency part of the S. You remember what's S? S is what? We call this the complex variable, right? Sigma plus J omega, right? This is the real part, this is the imaginary part. So we're going to, for the sinusoidal transfer function here, we're going to assume the real part is 0. So we're left only with this part, which is the harmonic part, right? This is the harmonic part. We call it the sinusoidal transfer function. Okay? All right. After this, خلاص, get your solution, the steady state solution. You know your solution will be always in this form. You will have an amplitude you look for, you don't know. And you will have a phase angle, you don't know. What you know already, you know your steady state frequency, which will be similar to the input frequency, right? Or the harmonic frequency or the driving frequency. Okay, and it will be assigned similar to the input. So how to find this one and this one? To find X, okay, X, the amplitude that you look for will be, okay, capital, will be the magnitude of your sinusoidal transfer function. So this sinusoidal transfer function, the magnitude of J omega times the magnitude of your input. Okay? Then you will get your amplitude. What's left? Left the phase angle. The phase angle you look for will be the same as the phase angle of your sinusoidal transfer function. Okay? That's all. How to get this? Let's solve this problem. Let's solve this problem, okay? Let's solve it together. What we need first, we need the transfer function. Okay, what's the transfer function of this model? Let me put it here. Remember the equation of motion? The equation of motion will be what? It will be, it will be, do you remember we solved it together? What's the equation of motion? mx double dot, mx. So first, what we're looking for again. Okay, given this system, okay, solve for the steady state solution. Let me remind you, okay, and also draw the steady state solution. Okay, we call it the frequency response. Okay, given, this is what's given, a second order system, okay, with the equation of motion that we will derive in a minute. Okay, what else given? Zeta in this system underdamped, zeta between 0 and 1. Okay, external force, P of T. This is what's given, P of T. How much is P of T? Sine omega T. Sine omega T. Let me draw this again here so we can follow together. You said this is X, and this is sigma, the spring, and this is the damper connected to the ceiling. K, B, X. What else? There's external force, he said. How much is the external force? P of T, which is given here. Also, he said the initial conditions, this is given in the problem. Initial conditions are equal to 0. Okay, is that all? Yes, that's all. Yes, the initial conditions. Okay, so this is given. Okay, find. This is what we're looking for. The steady state solution, and draw the steady state solution. Okay, solution. We're going to use sinusoidal transfer function, right? So step number 1. Okay, find the transfer function. The transfer function. Okay, it's in the S domain. How are we going to find the transfer function? Derive the equation of motion. It will be mx double dot plus k. Sorry, let me write it properly. Plus bx dot plus kx equal the external force P of T. Okay, this is the equation of motion. Okay, this is the equation of motion. Trying to refresh your memory about chapter 3. Now, how to find the transfer function? The input is what? P of T. The output is what? Displacement. Remember, it's underdamped, huh? It's always going to be underdamped in this chapter. Otherwise, we cannot do the analysis for the frequency response. Okay? So this transfer function we're looking for, the input is x. So take Laplace transform, assuming 0 initial conditions. This will be ms squared plus bs plus k multiplied by, this is k, huh? xs equal, this is a function, how, just say p of s like x of s, this is a function p of s. So the transfer function I'm looking for, which is what? The output x of s and the input is p of s, will be how much? It will be 1 over ms squared plus bs plus k, right? Remember, this is my transfer function with only variable, the s, right? The transfer function, it's in the s domain, right? Let me write it so you can remember. So this is what we got, the transfer function. Okay, this is step number 1. Step number 2, get the sinusoidal transfer function. What is t? Instead of s, I'm gonna plug in the sinusoidal part of s, which is j omega. We call this the sinusoidal transfer function. So the sinusoidal transfer function, just plug in j omega, and here plug in j omega. Okay, so it's gonna be how much? It's gonna be 1 over m j omega all squared plus b j omega plus k. Okay, all right, just evaluate calculate. What is j omega? J is a complex number, right? So squared, it will be minus negative 1. So it's going to be negative m omega squared. Plus, this is going to be j b omega plus k. Okay? Rearrange. Write the real part together and the imaginary part on the together. So this is going to be k minus m omega squared. This is the real part. Plus j b omega. This is the imaginary part. Right? And this is your sinusoidal transfer function. We're almost done. خلاص. Now, the last step, find your solution. Step number 3, find your solution. The solution, the steady state solution, it will be in this form, right? It will have a magnitude, I'm going to call it capital X naught. Sign, how do I know it's going to be sign? Because it's going to be similar to the input. This is the input, right? This is the input. Sine omega, similar to the input, omega t, plus a phase that I don't know. So what I'm looking for, this is I know already, right? This is we know from the solution. It's given here. It should be given, okay? This is a number, right? It's given. Okay, so this is given. What I need to find, only the amplitude and the phase angle. The amplitude, it will be how much? It will be the magnitude of the sinusoidal transfer function multiplied by the magnitude of your input, which is also given, right? This one is given. This one is given. Where is given? Oh, sorry. Should be here, okay? Should be given here. This is the magnitude, okay? Sorry about this. This is the magnitude. Should be given, okay? Like a number, okay? Like a number, 1, 2, 3. So this is given. What I know, what I'm looking for is this one. All right? I will show you how to find it in a minute, okay? And the phase will be simply, oops. Oh, made a mistake. I erased everything. No problem, I can do it again. Okay, it happens. Let me see. Yes, it's erased already. No problem. Let me do it again. What I'm looking for? I'm looking for the steady state solution. Okay, sorry. Let me call it again. This is step number, last step. Step number 3. Find the steady state solution. Will be X naught, capital, sine, similar to the input, omega t, similar to the input, plus a phase. Okay, this is given. Okay, this is what we don't know. How are we going to find X naught? It's going to be again the magnitude of the sinusoidal transfer function. Oops. Magnitude of the sinusoidal transfer function multiplied by the magnitude of the input p. This is capital. Trying to show you this is like capital. Okay, and the phase will be the same as the phase of the sinusoidal transfer function. Okay, how are we going to find this one and how are we going to find this one? I will show you. Okay, for the magnitude, the magnitude will be just like in math. If you learn math, the orientation math, algebra, and trigonometry, Tf j omega, the magnitude, you will have to find the magnitude of the numerator or the top over the magnitude of the denominator, which is how much? K minus m omega square. K minus m omega square plus j what? B omega. This is the imaginary part and this is the real part. You have to find the magnitude of the top over the magnitude of the denominator. Okay, so this is going to be how much? Magnitude of number 1 is number 1. Magnitude of a complex number or complex function is going to be tan inverse. Sorry, the magnitude, not the phase. The magnitude will be the square root of the real part, k minus m omega square all squared plus p omega all squared. Okay, this is the square root. So let me write it here again. ولا خلاص you don't have to write it again. خلاص, this is the magnitude. Okay, we solve it. It's a number. If you calculate it, it's going to be a number, by the way. If you have a calculator and these numbers are given, it's going to be a number. The magnitude will be a number. It's an amplitude. Okay, so now we know our magnitude. What's left? خلاص, this is, you can find it. This is given, this is calculated. What's left? The phase angle. The phase angle, how to find the phase angle of a function, complex function? It's going to be the phase of the numerator. Where is the complex function, the sinusoidal transfer? This is my sinusoidal transfer function, right? It's going to be the angle of the numerator minus the angle of the denominator, or the angle of the top minus the angle of the bottom, right? The angle of the top minus the angle the bottom, numerator or denominator, whatever you want to call it. Okay, so what's the angle of the number 1? Number 1, what is the angle of number 1? Remember how to calculate the phase, right? This is the real part, this is the imaginary part, right? This is the S-plane, we call it the S-plane. How to calculate the angle of number 1? Where is number 1? Number 1 is a real part, so it's like a vector here, right? This is like number 1, right? This is number 1. What's the angle of this number 1? It's going to be 0. Minus the angle of the denominator. What's the denominator? The denominator is a real number plus imaginary number. Real plus imaginary. So it's going to be somewhere here, right? Real plus imaginary, right? All of them are positive value. You can see that. Okay, so it could be here, right? Could be here. So how to calculate the phase of this number? It's going to be tan inverse, the imaginary part, which is b omega, over the real part, which is k minus how much? M omega square. خلاص. And this is your solution. Okay, it's going to be negative. This is 0. So now we got the phase angle. This is my phase, negative tan inverse. Okay, so now we know the phase and we know the magnitude. Now we know our steady state solution. خلاص, and that's it. This is the solution. It took me longer because I'm trying to explain, but if you do it by your own, it's going to be very, very short. Okay. So now you can check the solution. This is the steady state solution that we solved. Check the p, the magnitude is p over square root k minus omega square all square b square omega square. Let me check the solution that we got here. P, is it p? Yes, multiply by p. P times this, it's going to be p over. It is the same. That's good. Okay, so we got this correct. What about the phase angle? Should be also correct. So this is correct. The phase minus tan inverse b omega over k minus m omega square minus tan inverse b omega over k, which is also correct. So this is the steady state solution. We got it. Okay. So this is how the sinusoidal transfer function is working. Okay. You can also represent the steady state solution in terms of the zeta and omega n. If you divide the numerator by k and the denominator by k, you will get all the variables. Also here, if you divide by k, the numerator and the denominator, you will have your solution in terms of z, zeta, and omega n. okay, instead of B and K and M. Okay, same thing. Okay. All right. Now, how are we going to draw this? How are we going to draw this? The solution, you remember how to draw, right? You need always two plots. Okay. This is going to be omega, radian per second. This is going to be the same omega, radian per second. This is going to be the amplitude, X0, the amplitude. It's absolute value, there is no unit. Okay, and this is going to be the phase in degrees. Okay, in degrees. All right, the amplitude, when you start from 0, if you start from omega, the running frequency equal to 0, you will have same as we did last time. You will have static deflection. You will start from here. What about when omega equal to 0? When omega equal to 0, the phase will be also 0. Okay, because this is going to be 0. There is no phase if omega is equal to 0. Okay, if omega equal to 0, you can, if you don't believe, check with this one. If omega equal to 0, this is going to be 0 over 1. It's going to be 0. So for low frequency, okay, it's going to be 0 phase, no phase. Okay. When you increase the running frequency, when you increase omega for low frequency, you will have the same thing. You will have positive magnitude, similar to this one, positive magnitude. So the magnitude will increase until, I will use this one as better. Why? This is one better for analysis because we're going to compare it directly to omega n. So let's use this one. Okay. When you reach omega n, you will have a high magnitude now. Not going to go to infinity, but it will go to a high magnitude. Okay, here. Okay. All right. And when it reaches omega d, it will go to even to a higher magnitude. This is the peak. Okay. So this is the natural frequency. This is the damped natural frequency. It will go high. And this region, okay, this region we call it what? The resonance, huh? We call it the resonance that we are trying to avoid, huh, when we design our system. Okay, and here we will have a phase. If the omega is equal to omega n, you will have a phase here. It's not going to be equal to 0. This is omega. You will have minus 90. How do I know this? If you substitute omega equal to omega n, okay, this will be 0. Anything divided by 0, infinity, tan inverse infinity, it will be 90, and there is a minus here. It's going to be minus 90. Okay, so it's going from low frequency. Sorry, we have to connect the. It's not going to 0. Let me rearrange it. Here, starting from 0, right, at low frequency. Starting from here, it's going to 90. So if you connect them, let's connect them like this. Okay. All right. And what will happen if you reach a very high speed? If you reach a very high speed, this phase will become similar to the previous problem. It will be minus 180. Minus 180 degrees, which will be here at high speed. So you can connect them. And then it will continue at minus 180. I will show you in the next slide. Okay, we will have it nice using MATLAB. It will be much easier. Here also same thing. The magnitude. If you increase omega, it will have a negative slope. That means it will decrease until it goes to 0. So only difference between this one and the previous example, we have a peak here, not infinity, when we use the damper. And the only difference that we did here in this example, that we have minus 90 here, not a sharp jump between 0 and minus 180. There is a phase at minus 90. Okay. This is the nice plot using MATLAB. Okay. You see, this is the dashed line is the problem with a damper. The solid line is the problem without a damper. You see the difference between them? This is the natural frequency. This is the damped natural frequency. I think we made a mistake. Sorry about this. We switched. Sorry, we switched. The damped natural frequency always before. Okay? Always before. So this one, sorry about this. The natural frequency is after, huh? It should be after. After, not before. Let me. Okay. Always, because you can prove that mathematically also. So if this is going this way, okay. This should be what? This is omega d. And here after this a little bit. Just a small difference, huh? This is going to be omega n. This is omega n, correct, in the middle. But this one, no, because we have a damper. Okay. The peak frequency, this is the peak, the highest peak. This is the highest peak. It will be just below omega n, which is our omega d. The frequency or the natural frequency of the system with a damper. Which is this one, omega d. This is omega n. You see? Right after omega d. This is omega n. Okay? See that? So this is the resonance here, and this is the resonance for a system without damper. Okay? For the phase, what's the difference between the phase for a system with damper and without damper? For a system without damper, we have a sharp jump in the phase between 0 at low speed and minus 180 degrees at high speed. When we add a damper, you see the shift is smooth, more smooth. Okay, and this is good. The sharper the jump is, the higher amplitude you will get. This is not good. Your job as a control engineer or vibration engineer, you want to reduce the vibrations. So you want to add more damping, okay, to reduce the amplitude at the critical speed. All right. So this is what we call the frequency response. All right. So what we're going to do next, inshallah, we will see more examples and applications, see how useful the frequency response in more applications. The good news, there will be nothing new. You will see just more examples and applications. The most important topic in this chapter is how to find the steady state solution using the sinusoidal transfer function and how to draw the frequency response, the amplitude and the phase angle versus the input frequency. We call this the frequency response. All right. Thank you for listening, inshallah, and see you later.